Hi, and welcome to Calculus 30 with Miss Verity. Today we're looking at 5.6, curve sketching. Curve sketching is basically we are putting everything we have learned this whole course all together into one beautiful package. So things we want to find x-intercepts. We know that that is where f of x is equal to 0, or you're setting your equation equal to 0 and solving for x. Your y-intercepts, that comes from when you plug 0 in for your x and figure out what's your y equal to. Our first derivative, that helps us find some critical numbers, so where we have relative maximums or minimums, where our function is increasing or decreasing. We've also got the second derivative. That's going to help us find points of inflection. That will help us find our concave up or concave down. We also want to find those good old asymptotes and some end behavior. So what does that look like? First of all, beautifulness. That's the long and short answer of this. Okay, so we are going to graph the following. To start off, we want to find some x-intercepts. We know x-intercepts come from the numerator. So where does x cubed equal 0? Oh, lo and behold, 0. If we want to find y-intercepts, we're going to plug 0 in for our x. So 0 cubed over 0 squared minus 4. Well, 0 divided by anything? 0. So basically, we've got the point 0, 0, which is both our x-intercepts and our y-intercepts. Looking at our function, we know in our denominator, we are going to go to 0 at some point. That means we are going to have some asymptotes. So vertical asymptotes, that happens where our denominator goes to 0. So x squared minus 4 is equal to 0. You could factor. That also would be another way to solve this when we square root both sides. Plus or minus 2. So let's start this day off. Let's put some asymptotes into our function. So positive 2 and negative 2, of which, like I said, those backwards, but I think you can figure out what I wanted. So there's our asymptotes. From there, so our vertical asymptote, that comes from our denominator. We also want to check for our oblique asymptotes. So that's going to take some division. So x squared minus 4, we're going to divide. We've got our x cubed, so we multiply by x. So then we get x cubed minus 4x. When we subtract, we get 0, and we are left with negative 4x. Subtract negative 4, positive 4x. There we go. So what that means is we have a slope of 4. So this is what we're graphing. We're graphing y equals 4x as our oblique asymptote. So we know we have a y-intercept of 0. And then 1, 2, 3, 4 up, 1 over, 1, 2, 3, 4 up, 1 over, 1, 2, 3, 4 down, 1 over, 2, 3, 4, 1 over. Nope, I'm a silly goose. That is not what we have. That is not our asymptote. This is our asymptote. Just kidding. I knew something looked off. What a beautiful thing. So, there is our oblique asymptote. I'm just going to erase that. And let's put that in. Let's see if I can. Ooh, no. Try again. Try again. I don't know if I can edit it from there. What are the odds? Oh my gosh. Beautiful. Okay, there is our oblique asymptote. Those should be dotted. I just don't have that capability on my iPad. Okay, so from there's our asymptotes. And we know that that oblique asymptote happened because we have a higher power in our numerator than we do our denominator. So f of x, let's start with our derivative city. So x cubed, I'm going to change my look because I don't like the quotient rule. So taking our first derivative. We are going to get derivative of the first times the second plus the derivative of the second times the inside times the first, x cubed. So simplifying, what does that look like? We're going to take out a common factor of x squared and of x squared minus 4 to the negative 2. That leaves us with 3x squared minus 4 minus, we took out the x squared, we took out 2 of those x's, so we are left with 2x squared. Simplifying further, x squared minus 4, we now have 3x squared minus 2x squared is x squared minus 12. Which technically we could also factor that further. And that could be, I mean, if you want x squared minus 4 to the negative 2, let's not do that. We can just math the math. If you recognize this is a difference of squares. So our sign analysis on our first derivative, we've got a lot of things. We've got an x squared. You could do that as an x and an x. That's totally okay. We've also got x squared minus 4, which we could also leave that as a squared. We're going to put it as a positive just because it's positive in the denominator. And we've also got, I'm going to difference of squares that one just to ease our life. So it'd be root of 12, x minus root of 12, which is 2 root of 3, and x plus 2 root of 3. So we are going to 0 at x squared goes to 0 at 0. X squared minus 4 goes to 0 at 2 and negative 2. And 2 root of 3 is 2 times almost another 2. So it's almost 4. So this is negative 2 root of 3. And we've also got 2 root of 3. So that's where this one goes to 0 here. This one goes to 0 here. And this term technically goes to 0 there. Things that are nice, x squared is going to be positive no matter what number we put in. X squared minus 4, again, if we're squaring any number, going to be positive the whole time. In this last one, we are going to have negative, 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 positive, negative, positive, 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 positive. So overall, positive, negative, 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 positive. So what this tells us is our key points. We go from increasing to decreasing at negative 2 root of 3. Nothing else really changes until we get to 2 root of 3, where we go from decreasing to increasing. So increasing to decreasing, decreasing to increasing. So this function tells us we have a relative maximum at negative 2 root of 3. We have a relative minimum at positive 2 root of 3. We then also are increasing from negative infinity to 2 root of 3, and from 2 root of 3 to positive infinity. In between everything else, we are decreasing from 2 root of 3 to negative 2. Oops, I should not have closed that bracket. 2 root of 3 to negative 2. Then from negative 2 to 0. And then from 0 to 2. So that is what that function tells us. Now we want to check our second derivative. Again, to make your life easier, you can always, rather than having triple product rule, multiply those coefficients back in. So f prime of x currently looks like, for me, x squared minus 4 to the negative 2 and x to the fourth minus 12x squared. So second derivative from here. Derivative of the first times the inside stuff times the second plus derivative of the second times the first. I'm just going to double check that I did that right before we go on again. Okay. Okay, so far so good. So now we're going to take out some common factors. I'm going to take out a negative 4. Negative 4. This largest power is, I can just take out 1. We then want to take out the x squared minus 4 to the negative 3. And I think that might be it. So that takes this guy out. We took out the negative 4 and the x. So x to the fourth, we took out a negative. So minus 12x squared. That was the first term. We took out a negative here, so we're going to have subtract. We took out the 4x. 6, and we took out the x. And we are left with x squared minus 4. Things to remember, that negative has to distribute to all of that. Negative 4x, x squared minus 4 to the negative 3. We are left with x to the fourth minus 12x squared minus first, outside, inside, and last. Negative 4x, x squared minus 4 to the negative 3. So like terms, that cancels out. Negative 12, so this is minus 10x squared, so that is going to give me minus 2x squared minus 24. So with that, we can always take out more common factors. So I see that negative 2 is common. So 8x, x squared minus 4 to the negative 3. We took out a negative 2 plus 12. Okay, so sign analysis on this one. Sign analysis on our second derivative. Again, please always label your derivatives. It helps me figure out which one is what, because as you can see, we have a lot. So we've got an 8, we've got an x, which we could also treat as 8x. We don't actually have to do them separately. We've got x squared minus 4. I'm going to do that 3 times, because again, you could factor that further and have a heck ton of x plus or minus 2's and x squared plus 12. Where things go to 0, 8x goes to 0 at 0. X squared minus 4 goes to 0 at negative 2 and positive 2. And x squared plus 12 never goes to 0. It is positive the whole time. Let's start there. I guess I should put some zeros in. Oops. So negative, negative, positive, positive. Your x squared minus 4s, they look like this. So they are positive, then they're negative, then they're positive. Positive, negative, negative, positive, positive, negative, negative, positive. So negative, positive, negative, positive. So concave down, concave up, concave down, concave up. We have points of inflection. Point of inflection at, what is that, -2 and 2. And we are concave up. Sorry, I'm squishing this in. From concave up, -2 to 0, and from 2 to positive infinity. And then we are concave down from -infinity to -2, and from 0 to 2. Whew, okay, so what does that actually look like? We want to fill in our important pieces. So we know that, I'm going to maybe make this black. We have a point, our x and y intercept right there. Things to note, like, yes, though that is an oblique asymptote, but remember, within -10 to 10, that technically exists. It's when we go out to infinity. So we need, with our maximums and our minimums, here's my tip. I'm not going to do it for the purpose of this, but if you're wanting to put them in, we know that those are the x coordinates for our relative maximums and minimums. We'd want to find the actual y coordinate. So if we're plugging root of 12, I guess, yeah, we want to find our actual points. So let's go. Okay, so we're increasing and concave up from, so increasing and concave up. Oh, that's a very large point. I didn't want that. So increasing and concave up. We know that at -2, this is where our asymptote is. Same here. So that definitely helps us out. So concave down until we said it's about an x coordinate of 1, 2, 3, not quite 4. So increasing until there. We then start to decrease, but we are still, that is concave down. So that's okay. So we're still concave down and it'll follow our asymptote. So then from 2 to 0, we are decreasing. So in this entire middle stretch, we are decreasing the whole time. But with that decreasing from -2 to 2, we are also concave up to concave down, where we switch concavity at 0. So we are following our asymptote. We're going to be concave up. Ooh, if I can get closer there. And then we're going to switch to concave down following our asymptote. But the whole time we are decreasing. So that's awesome. Then from 2, so along our asymptote, we are decreasing until 2 root of 3, where we start to increase, and we are concave up the whole time in there. So what that would look like, so we're going to be at not quite 4. So again, find your actual y coordinate, but so we're concave up the whole time here, and we are decreasing from here to this is our 2 root of 3, where we start to increase. And so that is what our function would look like. I will do a Desmos practice question, this next one, in a different video because I'm going to run out of time and the bell's going to ring. See you there.